Let's compute the arc length along the graph of that equation over this interval. Well, looks to me like the length can be computed as such. I certainly do not want to use the other version for ds. That would give me a variable integration y, meaning I have to solve for x in terms of y, and there's no way to solve for x in terms of y mathematically speaking, so I will not go in that direction. Now, please pay really close attention to what's going to happen in the radicand's position. So watch me play. Differentiating with respect to x. Okay, I think that's showing up. I'm sorry, but I insist on using color, so watch me play with this. Yeah, that looks like it's decent. Now, with my red pen, I'm going to, oh shoot, this isn't going to work. Everybody, can I just put one small, tiny change in this? Very minor change. Much better. Now, take a peek at what's going to happen. When I expand this red binomial square, I get this corresponding red trinomial. And in removing this red set of parentheses, combining these two like terms, that is to say, combining the only two constants in the radicand's position, here's what it generates. I don't know how well it's showing for you, but I'm actually using, with this first term, my blue pen. I hope I've said this far too many times. I'm tired. I'm lazy. I don't want to do a lot of work. I don't want to have to think about how to factor this blue trinomial. So in allowing me to be lazy, notice that the blue trinomial here is exactly this red trinomial, merely with a sign change in the second term. So for free, is it not true that the blue trinomial is going to factor quite nicely into this red binomial? Quantity squared, but with a sign change in the second term. Now all of a sudden, I recognize my life is so darn easy. After all, these two cancel. I can easily anti-differentiate term by term. I think I can easily evaluate. Isn't that beautiful? We have just computed the exact length of the curve of the equation I initially gave you over the interval from 1 to 2.